recording. Okay, great. So yes, Arthur, should I look at, is that a Q&A or is that in chat, or do you want to ask the question?
No, so let's let it to the end. I believe it's better to after you finish this part as well, because there are many questions. So later you can have a look on them and decide which ones you can.
Sure. Okay, sounds good. All right, so let's continue. OPF as QCQP, and then semi-definite relaxations and some equivalence relationship among those. What we'll do is, for the first part, there are three pieces. One is OPF. So we will formulate OPF. So hopefully this, again, is a review, but we'll quickly go through them so that we're on the same page on, at least on the notation. And then what is the QCQP? And then OPF formulated as QCQP. So once we have a QCQP, then there's a very standard semi-definite relaxation of QCQP, which we can exploit to solve OPF. Okay, so in general, OPF takes this form. You want to minimize a certain cost subject to two sets of constraints. One is powerful equations, so we can use the complex form, polar form, or Cartesian form, whatever form powerful equations. And then there's some operational constraints such as voltage limits, line limits, stability limits, and many other things. But it's generally a constraint optimization problem. It's widely used for lots and lots of applications: state estimation, mobile control, DR optimizations, security constraint dispatch, and unit commitments, and capacity expansions, and many, many others. The details depends on, and therefore, if we look at this form, right, there are three things. What are the variables? So what's controllable? What's the cost? And then the operational and powerful equation constraints, right? So it's the variable, the constraints, and also the objective functions. So let's look at each of them. And of course, all of these depend on the applications, right? So there are three: the variables, cost function, and constraints. So the variables, again, it depends on which powerful equations, the forms that you use. So we're going to use the complex form, and therefore for us, there are two sets of variables, complex variables. So four real variables at each node. The real and reactive power, so Sj, small sj is a complex power injection. Sometimes we write in terms of P and Qs, and then the voltage phasor, like what we saw before in the powerful equations. The cost function can, typical cost functions can all be related to the voltage phasor. Right? So for example, and typically, we are going to use a quadratic form in the voltage phasor vector. So again, the VH is simply the complex conjugate. Right. So sometimes we write V star to be the complex conjugate, which means that each component of the vector is complex conjugate. So VH is the Hermitian transpose. It's a complex conjugate and then transpose, so it becomes a row vector. So for example, if we want the cost to be a weighted sum of the real power generation, this can represent the fuel cost. Then we can write, say, the cost to be sum of the generators J of some unit cost Cj, cost per dollars per megawatt hour, for example, times the real part of the Sj, right? Real part Sj is this. And this you can write in terms of the voltage phasor, sum over generator J, Cj of the real part of Yjk, the series admittance, complex conjugate. Let me use H to denote that. Sum over K of J and Vj square Vj Vk star or H plus Yj Km. So H Vj square. Let me do this. So let me write Yjj, which means sum over all the Yjkms. Okay, so the real part of this, and the right-hand side is simply a quadratic function of the quadratic function of the voltage vector phasor. So another example for the cost function is you want to minimize the loss, the total real power loss. Then this is over all the lines of the resistance on the line and the current magnitude square on the line. So again, this you can write in terms of the voltage phasor to be Rjk, Yjks, Vj minus Vk, Yjkm, Vj magnitude square, right? So the point is that the, that's fine. The point is that for most applications, the cost function is a quadratic function of the voltage phasor for some matrix C0. And typically we will assume C0 is positive definite, and therefore it has organized property, or at least positive semi-definite. In terms of the operational constraints, there are many, and we're going to consider only two. One is injection limit. So by this, okay, I should clarify what this means. Each is a complex number, and by this I mean the real part. So this really means two inequalities. There's a Pj that is bounded by its upper bound and lower bound, and then there's a Qj, the imaginary part of Sj, which is bounded by lower and upper bound. So that's what this inequality means. So it's it's here. It's injection limits. So let's say if the problem is to schedule generators, then this will be generation capacities, right? So the bounds, the lower bound, upper bound can be negative or positive, can be negative infinity and positive infinity, right? If they take in a negative and positive infinity values, it means there's no bound on the injection. In practice, of course, there's always bound, but it may not be active, and therefore, when we do the computation, we may be able to remove some of the bounds. It depends on the applications. So again, the powerful equations, let's say in the complex form, will relate the Sj with the voltage phasor. So everything can be expressed in terms of voltage phasor. So this is complex form that we saw before. And therefore, if we substitute this, if we substitute the powerful equation this into this, then we can eliminate the variable Sj. And it becomes a constraint on the voltage phasor, some nonlinear function, quadratic function of the voltage phasor. So this function needs to lie between the lower and upper bound, right? So this is in complex domain, and you can write this separately as real and imaginary part. And therefore, the capacity constraint is simply some function g of v less than some s under bar, less than s upper bar and higher than s under bar. And the voltage limit is very simple. It's simply this. Now this is non-convex because it looks like this. Right. So this is the region where the voltage phasor can lie. So this is real and imaginary part of the voltage phasor. the line limit is also this form. Some function of V lies between the line limits. And we saw earlier, if you can write this out, and it looks like this: yjk vj minus vk, yjk vj. So this is the line current from j to k, which may be different in the other direction. You pick the magnitude and say this is less than L bar. Right? So this is a form, and then in the other direction as well. Okay, so, and therefore, if we let the, let's say, let's call this V, the set V, to be the voltage phasor n+1, that will satisfy, so V, this vector will satisfy those limits, right? So this, so for us, we just consider the injection limits and also the line limits, but in practice, voltage limits and line limits, 3 of them, right? In practice, you will include a lot more other constraints, say ramping constraints and so on. So these are, let me just call limits. Capacity limits, voltage limits, and line limits, these 3 types, right? Then OPF is simply, you want to minimize certain costs. Let me just call C0 as a function of V. And again, typically we consider quadratic function with a positive semi-definite matrix. Okay. Minimize over V. Subject to the vector is in the feasible set. So that's OPF. The different applications would determine the details of this problem, but the structure is simply that. Okay, so that's OPF. Now QCQP, what is QCQP? This is quadratically constrained quadratic program. And it takes the form, the standard form is simply, you want to minimize over Cn, right? So this n-dimensional complex vector X. You want to choose X to minimize a cost, which is the quadratic form in X. So X complex conjugate transpose, that's X of H, multiplied by a certain matrix C0 and multiplied by the column vector X. So that gives you a scalar. In general, it's a complex scalar. We're going to assume all the matrices that we will deal with are at least Hermitian matrices. And therefore, the quadratic form will be a real number that we can minimize. Subject to XHCl of X. So that's, again, assuming CLs are Hermitian, then this is a real number, and we require this real number to be less than another given number B of L for, okay. So you minimize the quadratic cost subject to quadratic constraints. So it is specified, a QCQB is specified by the CLs, L from 0, 1 to L, so the set of matrices, and BL, L from 1 to L, and the scalars BL, right? So, so this is complex n, small n, in general, n by n. This is real, okay? So that's QCQP, the standard form. Now, if all the CLs are not only Hermitian, but positive semi-definite, then this is a convex problem. Now, the problem we see in OPF is here that, that for example, this function that represents the powerful equation is non-linear. But moreover, it is a quadratic form, but the corresponding matrix is not PSD. That's the problem. And therefore, we are in this regime. Otherwise, is non-convex problem. Okay, so we'll see more details of that right now. So let's put the OPF problem, which we formulated here, in QCQP format. And then we can see what the corresponding matrices are, the CLs are, right? So what are these matrices? The important things are matrices. And we'll see that it's not PSD. It's not even Hermitian. But that is easy to fix. And therefore, we get a non-convex problem. Okay, so let's do that. So we want to write OPF in quadratic form, where the cos, we assume the cos is going to be expressible as a quadratic form. So we saw that earlier, if it is, say, thermal loss, if it is, let's say, the fuel cost, for example, then indeed they can be expressed as quadratic functions of the voltage vector V. And then subject to a set of constraints that represent injection limits, voltage limits, line limits, and in practice, you can have many other limits. And they all can be expressed as quadratic form. So let me look at the time to see whether I should go through in detail. So let's see. Okay, so probably I should not go through in detail. Okay, let me just jump to the conclusion. The details are in the notes, but once you write this down, you will look. You will have the following thing. Illustrate how you actually do that. So we have the so we want to let me illustrate quickly this, how to write this as a quadratic form in the V. So we are looking at this equation. We're looking at this equation. So what is this equation? This equation is Sj as a function of complex form of the powerful equation V's. Okay. So how do we massage this so that this becomes a quadratic form? So let me illustrate that. So we start with, so what is Sj? Well, we know Sj is the voltage phasor times the current injection complex conjugate. So let me use H, right? So that's for Ij is a scalar, so the complex conjugate transpose, Hermitian transpose is simply its complex conjugate. But the key step is to write Vj as, which is a scalar, but write it as in terms of the vector. So what is this? So this is Ej is the vector where everything is 0 except for the jth entry. There's a 1. So transpose. Okay, and V is the V0, V1 to Vn. And therefore, the product, the inner product of Ej and V vector is simply Vj. That's what we want. Similarly, Ij complex conjugate or Hermitian transpose is same idea. I as a vector times Ej a vector. So that's all it is, right? And therefore, now the second step is to use write I. So I is YV. So you just substitute, you get EJ V V H YH Hermitian transpose and EJ. So that's the first idea. Write this, since this is simply a scalar, right? Sj is a scalar. And therefore, Sj is the trace of that, right? Because that whole thing is just a scalar. The trace for a matrix is the sum of the diagonals. That's the trace of a matrix. Right? So you write this out, you get EJ, VVH, YH, and EJ. Okay. So, but the trace has the property that the trace of, it commutes. So trace of AB for arbitrary matrices A and B equals the trace of BA. So you can swap the order. So that's what we do. We will swap which way? Okay, we'll swap this way. So we will swap EJ and the rest and move it here in one step. And then we do the next step, we swap YH and move it here. And the result of this is you get the trace of YH, EJ, EJH times VVH. And this is the matrix we need, which is an ugly matrix. It has a lot of zeros, just have one non-zero row. So let's call this Yj of H. And this becomes V Yj of V, right? And that's the quadratic form. So V is the vector, the column vector, row vector, and then multiply in the middle by a matrix, n+1 by n+1 matrix. And the problem is that okay, it is the Yj is not even Hermitian. And therefore it's not positive semi-definite. And therefore we get a non-convex QCQP. So the fact that it's not Hermitian is fine because you can look at the Hermitian component of Yj and the school Hermitian component. So you look at Yj plus Yj Hermitian, half of that. And then you look at Yj minus Yj 1/2i. So you can replace Yj by these two Hermitian, school Hermitian components. And the basically, if you multiply, you take the Hermitian form using these matrices, then you will get, this will be the real part of Sj, and this is the imaginary part of Sj. And therefore, you can put everything in terms of these Hermitian components of Yj into the form that we are familiar with, into this form, into the QCQP, where all the matrices C0 and C1 to CL are Hermitian. So they are Hermitian, but they are not positive semi-definite. And therefore, we get a standard form QCQP, but that is non-convex. Right, so that's what I said, that the CLs can be using these Hermitian, school Hermitian components, then we get the corresponding matrices to be Hermitian so that these are real. Powerful equations are not PSC. Okay, so that's step one. So we have looked at how we can formulate OPF as QCQP. Now let's look at the semidefinite relaxations and some of these properties. Okay, so let me yes. So let me go to my slides. So there's
Steven?
this. Yes.
Steven, we've lost your notebook.
Yes, that's right. Because I'm trying to get my slides, and then I will share my screen again.
Okay.
Yeah. Okay. So let me get to my slides. There's this. This readers. Okay, good. So it's going to be a course. Okay, good. Slides. Okay, great. Okay, so let me share my screen. Broadcast. Okay. Okay, good. So several different relaxations of OPF. I thought I can have a pointer. Okay. I thought there's a pointer. Wait. Oh, does it convert to? Sorry, it should open up as a PDF. Why does it? Oh, sorry. Let me. Oh, do I? I'm trying to. So you was open as PDF, but I want to open as PDF. The PowerPoint. So how does that work? Okay, let me do it again. Okay, let me do this. Right, okay, so let me go to this, open with PowerPoint. Okay. Anyone know how to, okay, maybe the file. Dropbox, no. How do I get my, oh, search, okay. Day 1, block 2, no result. Oops. Dropbox. Let me share my laptop. I don't quite understand why. Plot 2, OPF, okay. Okay, so let me stop sharing on my iPad and share my okay, so okay, good. All right. Okay. Screen sharing. Okay, so how do I remove this. Okay, great. Okay, so semi-definite relaxation. I won't have point. Okay, the cursor. Okay. All right, so the basic idea, and then we look at some concepts in linear algebra in order to explore the sparsity of the graph to simplify solving semi-definite relaxations of OPF. And then we look at some equivalence among the different relaxations. And then I will just mention the example applications, how this might be used. And there's a nice recent survey, a small book by Dan Mosen and Ian Hiskins that looked at these semi-definite relaxations and other relaxations and other issues in OPF, computational issues in OPF. So it contains a lot of information. Nice, very nice survey. Okay, so, this is the one, a survey of relaxations and approximations. Okay, so we saw this before. This is the basic idea. We can write OPF in this form where the objective function is this quadratic form, which we can write as the trace of this vector, this matrix. And this matrix has a C, which is a given matrix that represents the cost matrix. And then this V star. So V is a column vector, the voltage phasor. V star, I use VH sometimes, represents the Hermitian transpose. And therefore, V being a n+1 dimensional vector, the Hermitian transpose is a row vector whose entries are the complex conjugate of the vector V, right? And therefore, V star is a rank 1 matrix, is an n+1 times n+1 matrix that has rank, that is of rank 1, okay? On the constraint side is a similar structure. You have a certain Yj, which we saw earlier. On the iPad, I use YJH, or Hermitian transpose, but it's some matrix. Let's just call this Yj. For every bus J, you get a matrix. And then the VVH or VV star is again a rank 1 matrix, and Yj is it's a different Yj, right? Okay, it's a complex matrix, and this the trace of this matrix is less than or equal is bounded above and below by injection limits, and then the Vj square, the magnitude square, which is also a quadratic form, is bounded, voltage bound. And then you can have line limits and so on, as we saw before. It also can be converted into a quadratic form. So all those are functions of V. So the idea is that because Yj's are not PSD, post-semi-definite, we get a non-convex problem. And what we want is to look at the feasible set, this V that defines the set of vectors V that satisfy these constraints. This feasible set is non-convex set. And what we want is to rough informally design sort of a convex superset of V. So it's a superset that contains V, but it's convex. As we'll see, typically in a lifted space, but conceptually you can think of it like a superset. And then we'll minimize the same cost over this convex superset in a lifted space. Okay, and once we get an optimal solution of the relaxation, we check whether the optimal solution turns out to be feasible for the original non-convex OPF. If it is feasible, then it will be optimal because it's a minimum over a bigger set, right, in the lifted space. Okay, and that's exact relaxation. We call this relaxation is exact if that's the case. So what we want to understand is how do we design this, how do we characterize the feasible set V, and each characterization will suggest what is the right superset to use, and that corresponds to a certain relaxation. And then what's the relationship between these relaxations and when will a relaxation be exact. Okay, so let's focus on the feasible set, right? So the OPF relaxation all boils down to understanding the feasible set. So that's what the focus is. So one thing to notice is that everywhere the vector V appears, it appears as VVH. And therefore, we can think of VVH as a variable, which is a matrix, right? And in particular, we can equivalently write this QCQP as a minimization over matrix n+1 by n+1 matrix W, so that the cos CVVH is simply CW, right? The trace of it. It will be the same. The constraints will become these constraints in terms of W. Now, it's not any matrix W. The matrix W has to be positive semidefinite. So W greater or equal to 0 means it's positive semidefinite. And it has rank 1. Now, these two problems are equivalent in the sense that, given a V that is feasible for the original OPF, there is a W that will be feasible for the equivalent problem, right? W is simply VVH. In the other direction, given a V that is, given a W matrix that is positive semidefinite and rank 1, it has a unique up to a reference angle, but it has a unique decomposition into VVH. And that decomposed vector V will be feasible for the original OPF. And therefore, if it is not only feasible, but also optimal, then you get an optimal solution for each problem. Okay, so that's the equivalence. Now, the important thing is to know that the original problem is quadratic in V, but in the equivalent problem is linear in W for the constraints. So that's nice. The W being positive semidefinite, that's a convex constraint. The non-convex constraint is the rank constraint. Okay, and therefore a relaxation is simply to ignore the rank constraint. So later on, okay, we'll come back to this. So pictorially, what it is that you get a feasible non-convex feasible set V, and you can find a equivalent non-convex feasible set for the equivalent problem in terms of the matrices. And this W feasible set is simply a set of linear constraints intersect with the PSD matrix and rank 1. So if we ignore rank 1, then we get a convex set, which is a superset of the original W. Right? So W plus is a convex relaxation, which is a superset of W. So the QCQP has n variables, SDP has n square variables. So that's the cost. We get a convex approximation, so that's good, but at a much higher number of variables. So how do we reduce the computational burden for solving n square variables? Well, the one thing to note is that practical networks are very sparse, right? And therefore, that offers opportunity to really drastically reduce the number of variables that we have to solve. So the idea is here. In OPF, we solve for n variables, small n, which we have been using capital n+1 if there are n buses, n nodes. But for general QCQP, we use small n, and 1 at each node, right? So it's a complex variable, but n of them, 1 at each node. In SDP, we solve for n squared, right? So that's the issue. However, if we take a closer look at the constraints, it turns out not every entry in the W matrix is involved. It only involves very few number of them corresponding to off-diagonal entries that has some correspondence to the lines in the network. Okay, so let's look at that. So let's look at the feasible set more closely. And this trace of YJ VVH, if you write this out, it would look something like this. Now, what this says is that the only voltage that's involved, or the product of involved, are the Vj square and Vj Vk when Jk is an edge in the graph. If Jk is not an edge in the graph, then Vj Vk is not involved in the constraint. And this corresponds to, if you write in terms of the W matrix, this corresponds to the diagonal matrix, the diagonal entries of the matrix W, Wjj, and the off-diagonal entries Wjk only when Jk is a line, is an edge in the network, in the graph. Okay, and therefore, so this is linear in W's. Okay, that's fine. But the important thing is that very few, for the sparse network, very few of diagonal entries are involved in the matrix. So that's the idea, how we can exploit that. So there's only m plus 2m. M is the number of lines. M plus 2m variables, not n squared. So for a sparse network, m plus 2m can be much, much less than n squared. Okay, so in order to exploit this sparsity, we need the concept of partial matrices and completions and so on. So let's look at that. So what is a partial matrix? A partial matrix, Wg, which is defined on the graph G, is simply a set of complex numbers, right? So we're going to interpret it as a matrix that's only partially specified, but really what it is just a set of complex numbers. The set of complex numbers are defined with respect to a given graph G. So given a graph G, the set of complex numbers are the Wgjj, which means for every node in G, there's a complex number. For every edge Jk in G, there are two complex numbers, Wgjk and Wgjkj. So, and therefore, given a graph G, it defines a certain number of complex numbers. So we call them partial matrices associated with graph G and denote this by Wg. Okay. So one thing to know is that the Kirchhoff laws, which are the powerful equations, which eventually gives rise to these constraints, depends on this matrix W only through its partial matrix Wg. Okay, it doesn't depend on the off-diagonal entries that do not correspond to edges in G. Okay, so that's the important thing. So pictorially, it looks like this. For SDP, we solve for the entire matrix involving n square variables. But what we would like is to solve for only the partial matrices that involves only the diagonal entries of W and also the off-diagonal entries that correspond to edges in the graph. Okay, so that's what we like to do. Okay, so this is the OPF feasible set we saw before. This is the SDP feasible set that we saw before, right? So we get a linear constraint intersect with a requirement for the entire matrix to be PSD and RAM1. Now, this entire matrix involves every single entry in the matrix. And if you write all this out, it corresponds to a n-degree polynomial. So that's a lot. Now, what we would like is to do this, is to say, okay, let's only solve for those entries that corresponds to partial matrix Wg. Now, the constraints, the first set that describes the constraints, the powerful equations and operational constraints. So that's fine. You can define in terms of Wg. That's no problem. The challenge is the W greater or equal to 0 or PSD and RAM1 requirement. What we would like is to say, instead of requiring the entire matrix to be positive semi-definite and RAM1, we require only the partial matrix to be PSD and RAM1, which is a lot smaller set of polynomials to solve. Okay, so that's what we would like. This is fine. This is exactly exact correspondence, equivalence. if the graph G turns out to be chordal. So we'll see what it is. Otherwise, if the graph G does not have this property being chordal, then this is not equivalent. Okay, and therefore we need so the first idea doesn't quite work, but we can build on the first idea and make it work, and it looks like the following. So let's understand the feasible set, and then we will see how things work. So what is a chordal graph? A chordal graph is a graph where either there's no cycle, so it's a tree, that's chordal, or if it has cycles, any minimal cycle, that is cycles without chord, has length 3 or 3 edges. So that's a chordal graph, right? Every minimal cycle is of length 3. Okay. So it has a very nice property if a graph is chordal, because then given a partial matrix WG, if G is chordal, that is PSD. So what is partial matrix being PSD? What does PSD, positive semi-definite, mean for a partial matrix? It means that for every fully specified submatrix of that partial matrix, that fully specified submatrix is PSD. So we know what's PSD for a full matrix or fully specified submatrix, and therefore we can define what is a partial matrix that is PSD in terms of the PSD positive semi-definiteness of fully specified submatrices of that partial matrix. Okay. Similarly for RAM1. Okay. So so the chordal graph has a very important property where if the partial matrix of that chordal graph is PSD, then you can always fill out the remaining entries that are not specified to get a full matrix that is PSD. And therefore, in another word, if the graph is chordal, then a PSD partial matrix can always be completed into a PSD full matrix. If the graph is not chordal, this is not guaranteed. You may have a partial matrix that's PSD that you can indeed complete to a PSD full matrix. But you may also have a partial matrix that is PSD but cannot be completed into a full matrix that's PSD. And that's why the chordal graphs are particularly useful, and for us as well. Now, it turns out this completion applies not only to the PSD property, but also to RAM1 property. So that's the key result that we need. So consider a full matrix W, and consider its partial matrix W of G, right? Given the graph G, we can form WG, the partial matrix, right? And G may not be chordal. Now, for every graph G that is not chordal, you can always find a chordal extension, meaning that you can add edges to your graph so that you get a chordal graph. Chordal extensions are not unique. So given any graph that is not chordal, I can add sufficient edges so that the graph is fully connected. Fully connected meaning every pair of the nodes is connected. So a fully connected graph is chordal. Is a trivial chordal. It's very dense, right? So it's not the kind of chordal extension we want for computation, but it is a chordal extension. So chordal extensions are not unique, and what we would like is to find a, in some sense, smallest chordal extension of a graph G. So we'll come back to this point later. But given a graph G, you can form partial matrix WG. you can find a quarter extension C of G, which is some other graph, and you form the partial matrix of that quarter extension. That's WC of G. In terms of so each of them is simply, you can think of them as simply a set of complex numbers. W involves n squared of them, n squared complex numbers. WG involves n plus 2m, number of nodes, plus 2 times the number of edges of complex numbers. That's the WG. And WC of G, the caudal extension, the partial matrix defined on the caudal extension, has number of variables that's in between n squared and 2m plus 2m, n plus 2m. Okay. So you look at these three matrices. The first condition, that's the PSD condition, is that the full matrix W is PSD and RAM1. The second condition is the partial matrix defined on the caudal extension is PSD and RAM1. So again, we know what PSD RAM1 means for partial matrices. Again, it means that if you look at every sub-matrix of this partial matrix that is fully specified, then that sub-matrix is PSD and RAM1, right? That's what it means. And by the way, the fully specified sub-matrix in terms of the graph means that it's a clique of the graph. It's a subgraph that is fully connected, right? So that's what fully specified submatrix means. And the third condition is much simpler. Well, one aspect is much simpler, is you require the WGJK. So this is a 2 by 2 matrix. For every line JK, you get a 2 by 2 matrix, which is WJJ, WKK, WJK, and WKJ, 4 numbers. You require that 2 by 2 submatrix to be PSD and RAM1. So this is much smaller than the PSD RAM1 conditions above in C1 and C2. But there's a catch. There's additional constraint that has to do with the angles of the complex number WGJK around any cycle C. Right? So you sum the angles around any cycle that sums to 0. Right? So the angle difference sums to 0, mod 2 pi. Okay. So the main result is that these three conditions are equivalent. So what does that mean? It means the following. So this is a graph G. This is a quarter extension of the graph, right? It's not unique, and this is one of them. So every minimal cycle in this graph is of length 3. Okay. And partial matrix is this. It corresponds to every off-diagonal entry corresponds to a line. Okay. A partial matrix defined on the caudal graph is the same thing. It's the the off-diagonal entries all corresponds to a link in the graph. Okay, so C1 equals C2 in the theorem is that C1 equals C2 and equals C3, means that it means that the entire the full matrix W is PSD RAM1, if and only if this partial matrix defined on caudal extension of graph G is PSD and RAM1. That's what C1 equals C2 means. And therefore, instead of solving for W, we could solve for WCG. And so there's some entries that we don't have to solve for. Now, for this small graph, the savings in the number of variables is small. For large and sparse graph, the savings can be orders of magnitude faster. That in terms of computation, it's orders of magnitude faster than solving for the whole W, right? So it's very significant savings. And this is if and only if these two submatrices, that is the fully specified submatrices, are PSD RAM1. That's a definition of partial matrix being PSD and RAM1. And therefore, it's much smaller condition, the PSD and RAM1 conditions compared with the PSD RAM1 condition for the entire matrix, right? So you have a lot more, but much smaller matrices to deal with. So that's what C1 equals C2 mean. Much smaller for large sparse network. Yeah. C1 equals C3 means that the full matrix W is PSD RAM1, if and only if this much sparser matrix, submatrix, WG is PSD RAM1, and it satisfies that cycle condition. Okay, so cycle condition is also non-convex, unfortunately. And this means, so PSD RAM1 for the partial matrix simply means this set of two, there are 5 2x2 submatrices are PSD RAM1. And this condition is very easy to check, very easy to compute. These are 2x2s. The cycle condition is difficult. Now for a tree network, then the cycle condition is automatically satisfied. It's vacuous. And therefore, and we end up with a second order cone program. Right? So that's where the simplicity comes from for radio networks. So this is much smaller. Okay, so the 3 conditions are equivalent. Moreover, given a WG, the sparse partial matrix WG that satisfies this condition, there's a unique completion. What it means for OPF is that if we get a WG that satisfies C3, we can compute a unique optimal voltage phasor, unique up to a reference point, reference angle, that is optimal for the original non-convex OPF. That's what it means. Okay, so when WG satisfies C3, there's only one way to fill in the missing entries to get a full matrix W, from which a V can be recovered through spectral decomposition. Okay, so here's the conclusion. These 3 sets are the same, are equivalent in that sense, in the sense that given one, you can get a solution in the other set. And the non-convexities are RAM1, are the RAM1 conditions, and also the cycle conditions. So we're going to ignore them. Oh, cycle conditions, so let me skip that. So that's the implication of that theorem, that all these sets that we defined in the previous slide are equivalent. Okay, equivalent here means there's 1-1 bijection, 1-1 correspondence between the sets. Okay, so that's completion stuff. Let's ignore that. And therefore, in theory, we can just solve a problem that will minimize over any of these 3 sets. And of course, the challenge is that those sets are also non-convex, but the non-convexity are in RAM1 conditions and the cycle conditions. So we're going to ignore them. And therefore, if we ignore them, we'll end up with a superset that's convex. And that's the semidefinite relaxation. And therefore, instead of minimizing the cost over the original W or WC of G or W of G, we will minimize the cost over this W plus, WCG plus, and WG plus, which are the supersets that are ignoring those RAM1 conditions and cycle conditions. And then one can show that the original feasible set V of the OPF is a subset of these supersets, right? Those convex sets. For radio network, everything collapse. The W plus and WCG plus and WG plus all collapse. For mesh network, then the W and WCG, the partial matrix defined over caudal extension of the graph is equivalent to PSD. Much simpler in terms of computation, but it's equivalent. You don't lose any tightness. And therefore, for any network, if you want to solve semidefinite relaxation, don't solve SDP. Always solve a caudal extension. Solving for the partial matrix defined on a caudal extension of your graph. And this is important if you have a large network that is sparse. For small network, the difference is probably not too significant. for large sparse network, it's very, very significant. If it is a radial network, then don't even solve for the caudal extension, just solve for the partial matrix corresponding to your graph, because all three are equivalent. Okay, so for radial network, always solve SOCP. Because WG, when you ignore the cycle condition, is simply a second order Cone problem. So this is a visualization of what happened through some simulations. So the original feasible set is the black line. Is the black line just a line, nothing else, and so it's convex. It's non-convex. When you look at the SDP relaxation, the feasible set is the purple region that contains the black line, and therefore it's convex and it's a superset. SOCP is the yellow region that contains the purple region, and therefore the blue line. Now, if you blow up this region, okay, then what you see is that the boundary of the purple region is actually the black line. And therefore, if the cost is such that this is the Pareto frontier, then minimizing the cost over the purple region will give you an optimal point that happens to be on the black line. And therefore, SDP relaxation or the caudal relaxation is exact. It will give you a global optimal solution for the original non-convex OPF problem. However, if you blow up, and you will see that the yellow region will strictly contains the purple region and the black line. And therefore, when you solve SOCP, if the cost frontier is here, you will get an optimal point that is at the boundary of the yellow region, but not on the black line. And therefore, if you solve SOCP for this problem, which is a mesh network, you will get a solution that is not feasible for the original OPF. In this case, we won't get an optimal solution for the original OPF. We will get a lower bound in terms of the cost for the original OPF. Okay. So this is looking at the reactive, the real power. If you look at the reactive power, the same story. Okay, so recap, OPFs solve for n variables, SDP solve for n squared, but it's not necessary. We can solve the caudal relaxation that will solve for n plus 2m variables, which for large sparse network can be much lower than n squared. Okay, so this is just a summary. OPF is a problem that we want to solve. We can solve its relaxation, either the caudal relaxation for mesh network or SOCP for tree network. Okay, so this is just visualization of what we just went through. If you solve as semidefinite relaxations, so you're solving for these partial matrices, then once you get an optimal solution, you can check whether the optimal solution partial matrix is rank 1. And for SOCP relaxation on mesh network, you can check whether the cycle condition is satisfied. If they are, then you can recover an optimal solution for your original OPF. And there's a very simple construction from optimal solutions of your relaxations. Okay, for radial network, it's the same. Okay, so solve SOCP for radial networks. And it turns out even for three-phase network, this conclusion still holds. You can solve not exactly SOCP, but close to SOCP for three-phase network. Okay, so that's the summary. You can solve different relaxations. Once you get a solution W star or WCG star or WG star, you check whether the rank condition is satisfied. If the rank condition is satisfied and if the network is radial for this SOCP, then you're done. You can recover optimal solution V star. If it is, you're solving SOCP, but for a meshed network, then you also need to check whether your WG star satisfies the cycle condition. If it does, you're done. Otherwise, we get a solution that is sort of won't satisfy the Kirchhoff laws, and therefore it's not feasible for original OPF. So this set of simulations simply shows that SOCP can be much more efficient than SDP as the number of bus, as the size of the problem increases. Right? Caudal relaxation is similar. For large sparse network, it can be orders of magnitude faster than SDP. So this shows SDP for different number of buses. So this is Polish, 2,000 buses. That's Polish network. SDP, SOCP, and you can see that SOCP is, except for the 9-bus network, SOCP is inexact. Its cost is much lower than the SDP cost. And SDP for all these networks, we check is exact, so you get a global solution. SOCP is much lower and therefore is inexact. But running time is much smaller. So for large network 300 bus, SDP takes 109, SOCP takes less than 2 seconds. For 2,000 bus, so this is very early, almost a decade ago. So the code wasn't very optimized, and SDP did not converge. It's not scalable. For SOCP, it just takes 2 minutes plus. Caudal extension. So you can see that the caudal extension, the caudal relaxation is as tight as SDP, so you get the same objective value as SDP. But the running time is much smaller than SDP, orders of magnitude smaller for large network. Right? And therefore, again, to recap, if you have a radio network, just solve SOCP. If you have a mesh network, there's a trade-off. You don't solve SDP in any case. You can solve caudal relaxation. If that works, great, you get a tightest relaxation. If it doesn't work because it's still too large, then you can try solve SOCP. Most likely, if it's a mesh network, you won't get the exact solution. But there are other techniques you can apply to that and to try to say strong SOCP relaxation by Andy Sun at Georgia Tech, for example, that allows you to solve SOCP, but larger, much larger, potentially larger SOCP than this SOCP we discussed here, but still second order cone problem, and try to get a tighter solution. Okay, so let me just close by the advantages of relaxations. The traditional algorithm, the local algorithm, one is that it may not converge. So Newton-Raphson, for example, if the initial point is close to local optimal, then it's guaranteed to converge. Otherwise, it may not. And this does happen in practice. If you solve DC-OPF, there's no convergence issue, but the solution may not be feasible. Right? So there are other issues. Depends on applications. For some applications, DC-OPF is perfectly fine. For others, it's not. And also, for local algorithms, there's no guarantee on solution quality. Okay, so we'll actually come back to this point later on. But these are some of the properties with traditional algorithms. Algorithm based on convex relaxation. In theory, it converges. In practice, whether it converges or whether it converges fast enough, it depends on many factors: size of the problem, the condition of the problems, and so on. Right. So in theory, it should converge, and you should converge in polynomial time. Now, converging in polynomial time may or may not mean fast in practice. So we'll comment on that later on. But at least in theory, that's the property. That's a nice property that we have some theoretical assurance. Now, if it is feasible, if the optimal solution from the relaxation is feasible for the original problem, or satisfied RAM ones, cycle conditions, and so on, then great, we get a global optimal solution. So we not only get a feasible solution, we are also guaranteed that this we can do better than that. It's global optimum. Right? If it is not feasible, then in general, we don't get anything except a lower bound on the optimal cost of the original OPF. However, there are different heuristics. One can make use of this optimal solution. For example, you can use the optimal solution, which is infeasible, as an initial point to run your Newton-Raphson. And in practice, that seems to work very well, that very often you just converge and you converge to an optimal solution, global optimal solution. So there's some advantages on with relaxation approach. It doesn't solve all computational problems that we encounter in practice, but it is an important approach. Just one more tool in the toolbox. Also, the relaxation, because we have convex problem, leads to many interesting ideas. You can do tighter relaxations using this sort of hierarchy, high order semi-definite relaxations or using moments. You can have quadratic relaxations, which we'll cover at the end of today, which is a different type of relaxation, convex relaxation, but not semi-definite relaxation. The nice thing with that approach is that you can solve OPF that involve discrete variables, for example, using branch and bounds and so on. So that's a very nice feature of the quadratic relaxation that we'll see later on. You can make use of semi-definite relaxations to design distributed OPF algorithms. It also has multi-phase extensions to multi-phase unbalanced networks. Okay, so let me just quickly comment on applications. So one of the problems that we're seeing more and more in distribution systems as we have more and more PVs is voltage violations. So this is an actual experiment almost 10 years ago, back in 2013 on Hawaii. There's 68 residential meters, and they collected the measurements over 23 days in September. And you can see that the voltage violations are quite frequent. So that's a problem that we're seeing more and more. So almost 8 years ago or so, we worked with Southern California Edison, which is a local utility company in Southern California. And we looked at 6 of their feeders, 4 kV and 12 kV feeders. Together, they're about 15,000 buses, unbalanced 3-phase. And we built a distribution system model, power flow models and so on, and validated that model with the measurements from substation measurements. And it's reasonable. It's about less than 10% error. So it would be nicer if the error is smaller, but less than 10% is reasonable. Okay, so that's the set of feeders that we work with. And in particular, we look very closely and simulate quite extensively one of their feeders on which they know a lot of information. They know, for example, all the households. They even have socioeconomic conditions for those households, how many of them have PVs, how many of them have EVs, and so on. So this is 2012, and therefore the PV is relatively small. The number of PVs, the houses with PVs is only 16. Now it's a lot higher. And EVs, there are only a few households that have electric vehicles. It's a very small feeder. The payload is only less than 6 megawatt, about 1,400 houses, 100-something commercial and industrial buildings, mostly commercial, and about 200 transformers and 2,000 lines. So we built a model. It has about 2,000 buses and so on. What we looked at is as PV and EV penetration on the feeder increases, what is the voltage situation? Will it be unstable? Can we control smart inverters at the time it's not available in practice, but now there are products that allow us to control. If we can control smart inverters, HVACs, air conditioners, and so on the feeder, EVs on the feeder, and also pool pumps. Later on, we also look at energy storage, battery storage on that feeder. Can we control it optimally to minimize certain costs? And the different kinds of costs that we consider. And we use data from SCE to do 4-week simulation, 1 week in July, October, February, March. And we use actually unbalanced three-phase model to solve for the OPF. And then look at what would be the optimal control, and also how much savings in different, according to different metrics, can be achieved by optimizing DERs. So this is a very different kind of problem from the traditional control in the transmission network, where you control very few large bulk generators, to now you have to control many, many small DERs. Right? So that's the problem. We will look at this tomorrow, at the beginning of tomorrow, much more closely. So this is just one example how OPF, which is something like this we saw, QCQP, actually can be used for the for this kind of a DR optimization. Say for voltage control, for example, then if you write down the power flow equation, it looks something like this. On the right-hand side is the voltage, quadratic function in voltage we saw before in the power flow. On the left-hand side is the injection. And the injection, depending on the application for voltage control, can be broken down into the real power and the reactive power. In the real power, let's say if it's a node with a photovoltaic generation, then the PI is the load, which assume is given, let's say it's not controllable, unless you consider DR as well, demand response. But let's say it's not controllable for voltage control. PI is the generation from your solar panel that is also given. Let's say you have real-time measurement. The QI of L is the low reactive power. Let's say is given. The control is QI. So this is the control. That's the smart inverter. You can control the QI. And therefore, the PIL and QILs are background loads that are given, solar power PI that are measured in real time, and where you can control the QI. And therefore, you want to choose QI where you have smart inverters to minimize, to solve this OPF. That's, you can formulate voltage control as an OPF problem. And OPF is very versatile. You can capture different objectives, different control, and different operational requirements. Okay, so we'll look at this example, this Rossi circuit at the beginning of tomorrow in detail. I think I'm done. Okay, so that's the end of block 2. I think I'm running over, but the next one will be shorter, I think. All right, so we'll take a 5 minutes break now. Let me stop